Alright, so my screen recording software keeps crashing, but with that I've been able to chase out a couple of bugs in my computer program. So what this video is about is creating a fortran program for the Newton-Raphson technique. So we need a program statement, we need our double precision statement, and have a continuation character right here. I need to make sure we don't go further than 72 characters over without the continuation statement. I've defined my material properties, and if you notice I put a 0.0 behind them. Even though they're listed as double precision, it's always a good idea to put your numbers with a 0.0 if they are real numbers that you're dealing with. Here's my strain value, here is my initial guess that I'm taking, and then I'm just saying that my stress level is my guess. So it's just for clarity. I don't necessarily need that. I could have just put in sig is equal to 350, but I wanted to do this just to make the equation more clear. Now, we talked about these equations in the previous slide. Here's my F and here's my DF. My updated value of stress, sigma, is the previous value of sigma minus F over DF. And just for convergence reasons, I calculate a ratio, that's this term here, and I want to look at the absolute value of that ratio. If that turns out to be a really small number, that means I've converged. Now, what does a really small number mean for us? Well, in terms of stress, I've decided in my program that if I am less than 0.1 megapascals, I'm going to consider that converged. Okay, so if the ratio is greater than 0.1, greater than or equal to 0.1 megapascals, then I'm going to write the value of the stress out, and I'm going to go to line 100, which is to redo all these calculations with my new value of stress. Otherwise, if it is less than 0.1, then I say here's the stress and it's converged, and then stop and end. So again, a real simple fortran program. I'm going to compile that. G95, and then I'm going to run it. Now remember, it creates a executable called a.exe, and I have disabled my antivirus shield so it doesn't mess with my program. So here, this is exactly the thing that we got by hand, or the spreadsheet that I used previously. It calculates the ratio. The next value was 413, then it was 404.8, then it was 404.56, and then the ratio went from 0.2 to really small, much less than 1. And so then I hit my convergence criterion, and it outputs my stress value as 404.55. Okay. So in a similar way, we can develop a program for the branch equation, and this one's for the monotonic equation. We can develop a program for the branch equation, and we can develop a program for calculating the strain life. What I want to do next is I want to implement this as a subroutine for a larger Fortran program, and we're going to give that a shot. Okay, so I'm going to try to pause this video. If that doesn't work out, I may have to split this video and make a second video here for that. Alright, so I'm going to convert this into a subroutine, and it's probably going to take me a few shots. To get this correct, but let's just start out with subroutine nr, and I'm going to make a main program. I need to spell that right. Okay, now it's in that blue color. So I'm going to make a program called case1, and I want to see, let's copy this. Make sure I'm in column 7 here. And just to get started on our subroutine, let's say epsilon is equal to 2500 times 10 to the minus 6. Now right now I'm going to leave all these values hard-coded in here, except I'm going to take and get rid of this one. I want to get out of this I want to bring in my strain, and I want to get out of it my stress sigma. Alright, so if I've done this right, and I don't know if I have yet or not, it's going to call my Newton-Raphson iteration subroutine, and then it's going to send down into it the strain value, and then it's going to bring back from it the value of sig that I had over here. Alright, so I'm going to put in a write statement. I'm going to print out the value of the stress here. Alright, let's give this a shot. Yeah, case1.for. Didn't get any errors, so that's a good sign. And let's see. I think I need a different statement here. I need to get rid of that stop. And I think I need an end subroutine right there. Alright, so there it is. So it's as easy as that to incorporate a subroutine into a fortran program. So what this does then is all I do is I put my strain in here, and it goes through this, change this to subroutine NR. It's the name of the subroutine. My variables that go in and come out of my subroutine need to be defined. They need to be called that way. And then instead of stop and end, I have an end subroutine right here. Now, I could define all these material properties in here and throw them into the call and all that. You can do that. And I might change this later to incorporate all of that. But for now, this is sufficient. Alright, so we can do anything we want now with this. We can make this 3500 microstrain. Recompile it, and now we have a bigger stress. And now, since all this seems to be working, I'm going to get rid of these other kind of extra write statements down here, and I'm just going to comment them out. They were useful at the time, but now that it seems to be working, all we really need is that. And if you don't like all these digits, you can do a formatted write statement and whatnot. Alright, so we're going to work on this just a little bit more. We're going to, instead of calling this subroutine NR, we're going to call it subroutine mon for monotonic. I'm going to take and I'm going to copy this whole thing. I'm going to paste it. And I'm going to call it cyclic. I'm going to call it epsilon range and sig range. Okay, now I think I'm just slightly over. Let's get rid of a space or two. Okay, I can have my guess in here is 350, that's fine. Now my function is going to change a little bit. Let's see if I can pull up that slide. So my F is going to be my stress range over E, stress range over 2 divided by K prime to the 1 over N prime power. And I'll multiply that whole thing by 2.0, and I'm going to change this to the range. Let's see if that's what I got. Delta sigma, the stress range over E, plus 2 times stress range over 2 divided by K prime to the 1 over N prime minus the strain range. Okay, that looks good. My DF is going to be 1 over E. It's going to be 1 over N prime, 1 over K prime, stress range over 2, divided by K prime to the 1 over N prime minus 1. So my stress range is going to be my previous stress range minus F over DF. We can use a ratio of 0.1 again, and then that should do it. Okay, so now in my main function, I'm going to do this. This is the stress for the monotonic. Just going to copy these lines. Oops. Cyclic. Now I'm going to bring in my stress range, strain range, and I'm going to get out my stress range. My branch equation. This is my stress range from the branch. And for that, I'll make this 2500 again. my strain range and my stress range in here. And yep, that looks good. So let's give this a shot. We saw that should be like 809 or something about that from when we did this with the spreadsheet. Let me find my command window. And there it is, 809.11. Alright, so any other branch that we do after this is just for constant amplitude, is just going to have the same stress range. So there's all kinds of things you can do with this now. If you want to increment the strain range from one value to another, you can start at a delta epsilon of 1 microstrain and take it all the way up to 2500 microstrain. And you can compute the stress at every single location, just like we did in our spreadsheet. And then you can plot these in Excel. Okay, I'm going to let you kind of think about that and do that as needed. But this is basically what I want you to do for your project step 3 is to implement a Newton-Raphson iteration technique. If we had the fatigue properties, we can calculate a fatigue life based on all this as well. But I think this is sufficient for for project step 3, which is kind of a case 1 fatigue calculator. We're going to do all this kind of thing in more general terms for general variable amplitude loading. But we'll get to that soon enough.